All right, let's briefly talk about how the sun works, just as a brief overview. First, let's see, probably the first thing is we're going to be using some shorthand for the elements and isotopes. So first, let's make sure you understand how isotopes, or what isotopes are, and then how the symbols work. You probably know, or you can go back and review. The simplest element is hydrogen, and hydrogen has one proton in the center, and we'd said before that you have one proton and then there's one electron going around the outside, right? So there's the proton in the middle. The proton is positively charged, right? And the electron is negatively charged. That's what attracts them. We kind of did this already. Basically, the electrons are always circling the nucleus of the atoms, and the nucleus is where you find the protons and neutrons. It just so happens that hydrogen doesn't, this form of hydrogen doesn't have any neutrons. All right, here's the deal. There is a kind of hydrogen, a flavor of hydrogen, that does have a neutron. Here's another one. Also hydrogen is something that looks like this, but then it's got a neutron and then an electron circling it. So there's the proton, and then that thing, I'll just use a blue color, is the neutron. The neutron has no charge. Why is this still hydrogen? It's still hydrogen because it has one proton. Remember, the atomic number identifies an element, and that's just the number of protons. And all the normal matter that we'll talk about, the number of protons has to match the number of electrons because the atom as a whole has to be neutral. All the positive and negative charges have to cancel out. So hydrogen has one of each, and in all the normal matter that we'll talk about, if something has 6 protons, it'll have 6 electrons. 8 protons, 8 electrons, right? That number always has to match, and that's called the atomic number. That's how we differentiate one element to another. That's what makes one element different than another element, is the number of protons and the number of electrons, because they have to match. Okay, that's called the atomic number. What could happen? Oh, that's why, by the way, the second thing is also hydrogen. It still has one proton. What we do is that we give it a symbol like H. And H tells you, that symbol tells you the number of protons, right? Because the number of protons tells you what element it is. So each element has its own sort of chemical symbol. And sometimes you probably will have to look that up until you get familiar with it. But that letter, or the couple of letters, tells you how many protons are there. Okay. The ambiguous thing is that you don't know how many neutrons might be there, because both of those things are hydrogen. One has no neutrons and the other thing has one neutron. So what we do is we just count the number of particles in the nucleus, protons plus neutrons, and that's this. That's not clear at all, is it? That's sort of between a 2 and a 3. It's supposed to be a 2 there. It's not much better. So that's got 2 particles in the nucleus. The superscript is number of protons plus number of neutrons. So for that kind of hydrogen, it's got 2. So we call that hydrogen 2. By the way, this also has a nickname because it turns out it's really important, and this is just called deuterium. You won't find it if you look on the chemical elements. This is what's called an isotope of hydrogen. Iso meaning same, and tope, type, same type. So it's still hydrogen, but this one is so important that we give it a nickname, and we called it deuterium. Du for like duo, because it has 2 particles. Okay, so what happens if we have 2 protons? How about this? What if we have something like this? What if I have 2 protons? And here's sort of a problem, and we'll get to this. Already, a toddler question might be, how do you get something like this? If I have 2 protons, this is going to be helium, right? Helium is element number 2. How does this even work? Because those 2 things are positively charged, and 2 positive charges that close together, they're going to repel each other, right? So how does helium stay together? And the answer is that it needs help. It needs help from these things. Oops. The extra neutrons. You can kind of think of it that the extra neutrons form a kind of glue. They help form a kind of glue. It turns out protons help with the glue also. We'll talk about that in a minute. But this is the only way that helium can stay together, is if you have these extra particles helping it stick, because those 2 protons are repelling each other. The neutrons having no charge, they don't repel each other. So the helium nucleus can stick together because they have all this extra glue. That glue is called the strong force, the strong nuclear force. It's a really short-range force, and we'll talk about it in a minute. Okay, but anyway, this is a kind of helium. So the chemical symbol is He. And then you just count protons plus neutrons. How many are in it? 4. There's 4 things there. So that's helium-4. That's how we write it. We know, so this also means that it has, if you just see helium-4, you know almost instantly it has 2 neutrons. Because it's helium, it's got 2 protons, and the total number of particles is 4, so that means there's 2 neutrons. That's how that works. What if I would write down carbon 12? Okay, carbon, you can look up on the periodic table. Carbon is element number 6. So it's got 6 protons, definitely. And if the total number of particles is 12, that means that carbon has 6 protons and 6 neutrons. There's a type of carbon that is unstable. Carbon 12 is stable. There's a kind of carbon, isotope of carbon, called carbon 14. Carbon 14 is still carbon. It still has 6 protons, otherwise it wouldn't be carbon. But now this must then have 6 protons, 8 neutrons. It turns out this is unstable. It sounds weird though, because that shouldn't make much sense to you, because that's like it has too much glue. So wouldn't that make it extra stable? Turns out no. Turns out quantum mechanics tells us that this is unstable. So anyway, that's how we use the number above the chemical symbol. So the 14 tells us 6 protons and 8 neutrons. So by knowing the chemical element symbol and then the number, you can write down how many protons and neutrons the thing has. Generally speaking, most isotopes are unstable compared to the sort of regular element. Okay, so that's how isotopes work. So I wanted to get that out of the way in case maybe you haven't seen it in a long time. But it'll be kind of essential to what we talk about now. Okay, which is how the sun works. So, how does the sun work? Let me write down a maybe. And they cover this in the book. People have had ideas for thousands of years of how the sun works. And it really does look like a great fire in the sky. And it's it looks yellowish, and you can feel the warmth. So people have often thought that maybe the sun really is a fire in the sky in the same way that you can build a fire in your fireplace. Maybe it's a fire. Okay, that's possible. It's an idea. In science, though, ideas have consequences. What if it's a fire? Well, you have to follow that through. In science, in order to lift an explanation up to the level of being a theory. Remember, in science, a theory is something that is really well tested. We think it's probably correct, at least as correct as we can get it for now. So theory is very strong in science. It's not just a guess. A guess would be, this might be a guess, it might be a hypothesis, that it's a fire. But in order to elevate this idea up to a strong explanation or a theory, in science we demand two things. We demand that something has to be plausible. In other words, the math has to check out. Could this possibly be the source of the sun's energy? Is it even plausible? And the second thing is we want this. We want evidence. If we get those two things, that's a pretty good explanation. It's hard to argue with. So first of all, is it a fire? Is it plausible? Well, the book goes through some of the argument and even the calculation. It turns out that we can calculate. We know the sun's mass. How do we know the sun's mass? Because we can watch the planets go around it. And so from Newton's laws, we can calculate the mass of the sun. So in other words, we know how much fuel there is. Right? The mass of the sun. If all the sun were to be used as fuel, we know how much that is. We know the rate at which the sun burns. We know the sun's luminosity. We can measure that. We talked about that last week, right? So we can measure the luminosity of the sun, which is the rate at which it burns energy. So if we know how massive the sun is and the rate at which it burns energy, it's almost like figuring out the range of your car's gas tank, right? The miles per gallon is the rate at which you burn fuel, and the total amount that's in the tank, that's like the mass of the sun. So you can calculate how long can I go on a tank of gas. You can do the same thing for the sun because we know the rate at which you get energy out of burning things. We can measure that. And the book says, and that's right, when people did this, finally in the 1800s, we could measure the amount of energy you get from burning. And the trouble is, when you do this, even if the sun used its entire mass in burning, the sun would only be able to be a few tens of thousands of years old. And already by that time, already in the 1800s, you know from studying the Earth that we knew about fossil formations, and we started to understand geology, that the Earth was ancient, hundreds of millions of years old. Now we know it's billions of years old. But already this idea was in trouble. So was it plausible? Nope. Because it couldn't explain the long lifetime of the sun. Even if it could, here's also what you're stuck with. If the sun really were burning wood or oil or coal for energy, what's the evidence? Well, what happens if you do that here on Earth is that you have, what's the evidence that something is burning? How do you know your car is running? Maybe it's a really quiet engine. But somewhere, usually in the back of the car, you have exhaust, right? There's some byproduct of the burning. There's some evidence that the engine is running. So around the sun, if the sun really were burning, we'd expect to see evidence of it, like a big cloud of smoke, right? Byproducts of burning. Carbon monoxide, water vapor, sulfur compounds, all the things you get out of your tailpipe from burning. So when we look at the sun with spectroscopy, where we can identify particular elements that are around, do we see these things in a cloud around the sun? And the answer is no. So not only is that idea not plausible, it can't account for the lifetime of the sun, there's no evidence for it. We should see something and we don't see it. So this idea that the sun really is sort of a fire, we just sort of throw out. It can't be that. So that meant in the late 1800s, early 1900s, it was a puzzle, right? It was a big scientific puzzle. How does the sun work? It's embarrassing not to know, right? Toddlers might ask you the question, how does the sun work? And before about 90 years ago, no human on the planet knew what the answer was. They could not have possibly known what the answer was. But now we think we know the answer. Here's what happens. The reason that we figured this out 90 years ago is because we did experiments in what were then called atom smashers, right, particle colliders, and we figured out something really interesting that happens. if I get a proton and a proton, and these two things are running at each other, maybe they're going really fast. In the center of the sun, they're going to be going really fast because the center of the sun is like 15 million degrees. So remember, temperature is just indication of how fast the gas molecules are moving. In this case, it's mostly hydrogen. So the protons are moving really fast in the center of the sun, which means that at that temperature, they can come really close together. Now, the problem is they're positively charged, right? So they're repelling each other. It's like trying to bring two north poles of magnets together, where normally they would repel each other and then go off in some other direction. They would just sort of miss each other. But if they're traveling fast enough, it turns out that they can get close enough for an amazing thing to happen that we didn't know about until we ran the experiments. It turns out that there is another force that nobody knew about. And this is that strong force. It's a very close force, and you can think of it as, it's not this, but you can think of it as almost like little Velcro hooks around the outsides of the proton. Of course, it's not like this, right? But it's just in your head. This is the way you can think about it. In the same way that if you coat a couple of balls with Velcro, they're not going to stick together until you bring them very close, right? And then when you bring them some critical distance from each other, the little Velcro hooks latch onto each other and they stick. Protons, it turns out, have this ability to stick together. They have this close range strong force that slams them together. It's called the strong force. Astronomers are really good at naming things. It's called the strong force because it's stronger than the electrical repulsion that's trying to push them away. But it only happens if you get them close enough. What's close enough? It turns out it's about the width of one proton, coincidentally. Roughly, that's right. So when they get that close together, the strong force takes over and these two protons smash together. Oops. I'm all excited and I can't draw. Okay, so the two protons smash together and you get something like this. Okay, so, I mean, that kind of looks like helium, but it's a weird helium because there are no neutrons there. What nature does, there are little loopholes in nature that we didn't know about. We had to figure them out through experiment. What happens is that nature can do a little trick. It turns out these two protons are sort of repelling each other. There's a little bit of energy lost there where they're trying to repel each other. And nature has a little trick. And the little trick is, maybe you didn't know this, a proton can turn into a neutron. They can turn into each other. They can change. So I can go from a proton, I can go from a proton and a proton to a proton and a neutron. That could happen. And it does happen because this is a little bit lower energy. Notice this is a little more relaxed, right? Because the proton and neutron are only attracting each other. Neutrons have this strong force just like the protons do. So the proton and the neutron are stuck together with this strong force and they're not repelling each other at all because the neutron doesn't have a charge. So nature likes this. It's a little bit lower energy state. So this could happen. And this is that cool thing called deuterium. Notice that's just a hydrogen 2 nucleus, a proton and a neutron together. Okay, so that's what happens. But now you don't do this, nature doesn't do this for free. There's a few rules. One rule is apparently, and again, nobody knew these rules until we did experiments and we started noticing that this was part of the game. You can't destroy a charge. So it looks like we've destroyed a charge. We've gone from 2 plus charges to 1 plus charge. Well, it turns out nature doesn't like that one bit. So what happens is that this proton turns into a neutron, right? But we've lost a charge. So what nature does is it creates an interesting little particle called a positron. This thing is exactly the twin of the electron, except that it's got the opposite charge. In fact, this is called antimatter. This is our first exposure to what we call antimatter. It's exactly like an electron in every way, except that it has the opposite charge. Its nickname is a positron. And notice now that everyone's happy because we start off with one positive charge on the left, and now we have one positive charge on the right. So that's called conservation. Charge has been conserved, so everyone's happy. By the way, what happens to this thing? This little positron, notice it's going to be really attracted to a negative charge like a regular electron. And in the center of the sun, there's all sorts of regular electrons just bouncing around because it's so hot they've been stripped off from the hydrogen atoms. And so there's just ordinary free electrons just bouncing around. And so it takes almost no time at all for this positron to find an electron because they're attracted to each other. And when they combine together, what happens? You might have heard that when you combine matter and antimatter, what happens? They totally annihilate each other. And so what you get is an intense flash of light in the gamma part of the spectrum. What you get is a gamma ray, a really highly intense flash of light. So that positron, in no time at all, it's just gone. It annihilates with an electron, and then you get a gamma ray. Okay, we're not done. Here's something not obvious, is that what nobody knew is there's another rule, and the rule is you can't, the electron is a member of its own sort of a particle family, and they always come in pairs. You can't just create one. You're like, why not? And I'm like, because you can't. It's a rule, right? It's a rule of nature. So what has to happen is another member of this family has to pop into existence, but it's got to be a weird one because we've already taken care of the charge. This can't have any charge on it. And in fact, this little guy is called a neutrino. Neutrino, just coming from the language, just means little neutral one. And it's a little tiny ghost-like particle that we'll talk about in a few minutes that streams out from the interior of the sun. It's a byproduct of this reaction. Okay, step back. What did we just do? We have two protons got close enough to fuse. Right? Fusion is when you combine things together to make a larger thing. Fission is a type of nuclear reaction where you're taking like a big thing like uranium and you split it. So this is nuclear fusion. So two protons fuse together, and then one of those protons turns into a neutron, and you get this hydrogen, you get this deuterium. Cool. Okay, there's a couple of other steps, but I want to kind of skip ahead. Because the other steps I'm not terribly interested in. Except to say that if this thing finds another one, because this is happening all over the interior of the sun, if this happens to find another one, here's roughly what happens. I'm skipping over a step. If you look up this step, this is called the proton-proton cycle in the book. I'm going to skip over a step. What ends up happening, the net result of this, is that when two of these things get together, look what you're going to have. You're going to have a proton and a neutron fusing together with another proton and a neutron. And what you get is helium-4. Right? You just get a helium-4 nucleus. You get basically this. Two protons, two neutrons. Neat. So the net result is that you get four... Oops. I want to write it like this. I want to be careful that that's not a superscript. 4 hydrogens. That's not a superscript. I mean 4 hydrogens protons combine to form, that one I do mean to be a superscript, a helium. So I take 4 hydrogens, I fuse them together, and I end up getting a helium. Now there's another couple of steps in there. You'll see there's like helium-3 is made and so on, but it's not terribly important for us. The net result is that you get 4 hydrogens combining to form a helium. Okay, cool. So if you follow all that, that sounds great. But where does the energy come from? And here's a neat little fact. Helium weighs about 1% less than the 4 hydrogens, the 4 protons. And that's a little weird, right? I mean, if I took 4 ping pong balls and I weighed them and then I stuck them together, I would be very surprised if the final thing weighed less than the 4 ping pong balls individually, right? Where did the mass go? Well, it turns out that when you do this, that's what you get. The helium weighs a little bit less than the 4 hydrogens, about 1% less. And where does the mass go? Einstein said, in the most famous formula in all of physics, that energy, the E, energy, the amount of energy you get from a mass m is multiplied by the speed of light. This is the speed of light squared. That's a huge number. Speed of light's big already. And then you square it. So the upshot of this is that a little mass gives you lots of energy. So that 1% of missing mass is radiated out in the form of energy, that gamma ray plus others. So that's where the mass goes. So when you make helium from hydrogen, you release energy. And that's exactly what we see. So this idea of the sun using fusion to produce energy, is it plausible? Well, it turns out you can figure that out. You can calculate. That's a calculable amount of energy. So if you calculate that by all the atoms available in the center of the sun to undergo fusion, what you wind up with for fusion, what you wind up with for fusion is that, yep, it's plausible because you get a possible lifetime of the sun of about 10 billion years, which works out great because the sun is about 5 billion years old. So the sun is about halfway through its life. So fusion is plausible. It can account for the long lifetime of the sun, no problem. It's much more energetic than just burning. This is why, by the way, we're so afraid of nuclear weapons, that we have done this. So this doesn't just take place on the sun. We've actually done this on the Earth. Where was this done? It's done in the middle of hydrogen bombs back in the 50s. I don't even think we test them anymore. But back in the 50s, we figured out how to do this. And of course, the first thing we do is make bombs out of it. But it's a million to 10 million times more energetic than just ordinary explosives, which is why we're so scared of nuclear weapons. But this is how stars work. In a real sense, we made a teeny tiny star when we set off these bombs. Okay, so fusion can account for the long lifetime of the sun. It's very energetic. Now, the second part, what about the evidence? What evidence can we see that this goes on? Maybe you think, well, this all sounds weird. I mean, how do we even know this is happening? It's a good question because this happens at the center of the sun. It's not like you can go there and see it happening. So are there any byproducts? Is there any sort of exhaust that we can see from this going on? Well, we already said that you're not going to be able to see the positron because it combines right away with an electron and makes a gamma ray. And the trouble is those gamma rays right away, they hit a particle and then they start degrading on their way out. So you can't see it. The sun is opaque to gamma rays. So you never see gamma rays streaming out of the core. So we can't see those. But what about these guys? Neutrinos are so tiny and they're not charged, so they just float right through ordinary matter. Remember we said that matter is mostly empty space. I always talk about things not being to scale, right? Whenever you draw an atom, the electron is never to scale. The neutrino sees that scale. It sees atoms as almost totally empty space, and it can float. One neutrino can float through light years of lead without encountering anything. It just floats right on through. So neutrinos, these neutrinos, if this is really what's going on, we should be able, if we can detect them, we should be able to see them streaming out from the center of the sun. That would be good evidence that this is some sort of nuclear reaction like this is really taking place. But the trouble is they float right through everything, so how are you going to detect them, right? In order to detect them, you have to stop them. In order to figure out they're there, or they just float right through your detector. So in the book, you'll find pictures of giant neutrino detectors. And these things were made in salt mines miles below the Earth's crust, abandoned salt mines. And they're fascinating things. It's basically chambers of liquid, and they have these cameras arrayed miles underground so that only neutrinos can make it down there. And every once in a while, neutrino will hit something. And when it does, there's a little flash of telltale light that we look for. That's what all the cameras are looking for. So in the 60s, starting in the 60s, we built these giant neutrino detectors all around the planet. I think there's 5 or 6 of them, looking for these solar neutrinos. And long story short, and we might come back and talk about how this was a puzzle at first. But anyway, the upshot is we found them. Oh, we will come back to it. When we talk about massive star evolution next week, I will have a little bit more to say about them. But anyway, we're able to see them. So there are neutrinos streaming out from the center of the sun, and we've detected them. So now we know that it's not just plausible, but we actually see the evidence. We can sort of see what's going on in the center of the sun by looking at these neutrinos that are streaming out. So this apparently is how stars work. The stars are combining. We'll go with this right now and then we'll modify it as we go along. But the stars are combining light elements to form heavier elements, and when they do that, they release energy. So this is how, this is what's going on in the center of the sun. How much mass is the sun losing in order to shine like this? It sounds scary because it turns out the sun is losing, I think it's 5 billion kilograms, like 10 billion pounds every second. Every second that goes by, the sun just lost another 10 billion pounds. That sounds alarming, but the sun is so massive, you can just calculate it yourself. How long can the sun go on losing, with the sun's mass, how long can it go on losing 5 billion kilograms every second? It turns out it can do that for about 10 billion years, not coincidentally. So, no problem. The sun's losing lots of mass, but the sun is so massive that it doesn't make any difference for a few billion years. Okay, so next time we'll start talking about what happens when the sun runs out of fuel, because it's not going to last forever.